and running now. Okay, here we go. All right. What is data? Well, data are nothing more than measurements or observations that are gathered for the purpose of conducting some sort of a study. Now, measurements may be qualitative in the sense that they may not be numeric, or they could be quantitative. More normally, data is quantitative, okay, numerical, but not always. Sometimes our data is, non-numeric. Okay, we call it qualitative as opposed to quantitative. All right. What is statistics? Ladies and gentlemen, statistics is a science. It's a branch of mathematics that basically involves collecting data, organizing your data, either using tables and or graphs or pictures, and then conducting some sort of an analysis on the data, especially if you get into the branch of statistics known as inferential statistics. In inferential statistics, what we do is we reach into a parent population and pull out a good, simple, random sample from the population. We calculate some result from the sample and then use that result to try to infer something about an unknown population parameter result, okay? And for instance, if I wanted to determine what an unknown population mean is, all right, and let's say my population has millions of data points in it. Well, I may not have the time and or resources to go out and pull all of the million, data values in my population to determine the mean. So how do we do it if we can't go out and pull everything in a population? Well, oftentimes, ladies and gentlemen, we resort to what's called a sample. We reach into the parent population and pull out a good random sample from the population. We then compute something from the sample and then try to use that to infer what an unknown population parameter is. Now, would it be good enough if I reached into my population that had like millions of data points in it and pulled out a sample of size, let's say 10,000, computed the mean of that sample? Do you think that one sample mean would accurately indicate what the unknown population mean is for all of the millions of data points? Anybody want to take a wild guess? Do you think that one sample mean is accurate enough to infer what the mean is for our entire population, which could consist of millions of data values? And you said no, correct? And you're right. I mean, a sample mean is a rough guesstimate. It's a rough point estimate, we say, of the unknown population mean. But ladies and gentlemen, the weird thing about this is if I reached in and pulled out another sample of size 10,000 and computed the mean for that sample mean might be different than the sample mean was from the first sample. And if I reached in and pulled out another sample of size 10,000 and measured its mean, then that third sample mean might be different than the first two sample means. So my question is this: which sample mean would you use as the accurate assessment or the accurate value for the unknown population mean? Well, we don't have a clue. Do you agree? In fact, if you have millions of data points in your population, there might be thousands and thousands of samples of size 10,000 you could extract from the parent population, each of which would have a different sample mean. So which sample mean would be the accurate, guesstimate as to what the unknown population mean is? Well, we don't know. And for that reason, one sample mean is just a very, very rough, crude guesstimate as to what the population mean may be. To be more accurate, ladies and gentlemen, we would have to go a little bit deeper into inferential statistics and construct what is called maybe a confidence interval, or actually conduct what's called formal hypothesis testing in statistics to determine or infer from our one sample mean what the unknown population mean is. And the nice thing about building a confidence interval or doing hypothesis testing is that we have a measure as to how accurate or inaccurate that one sample mean is in identifying the unknown population mean. And that hinges on a very powerful theorem in statistics called the central limit theorem, okay, and something called a sampling distribution. All right, so Statistics basically consist of collecting data, organizing the data, and maybe reaching in and pulling out a simple random sample from a population, and maybe building a confidence interval or conducting hypothesis testing to infer what an unknown population parameter is, such as what the unknown population mean might be, or the unknown population proportion might be, or the unknown population variance or standard deviation might be. Okay. Also in statistics, we touch base with correlation and regression as a nice way of modeling data according to a linear algebraic equation. And then once you have your data modeled according to an equation, you can then use the equation to make useful predictions or forecasts. Okay. So statistics is a science. All right. Now, the first thing we need to usually come to grips with is, what's the difference between a population and a sample? And it's pretty easy to understand the difference. A population, ladies and gentlemen, consists of all subjects that are under study. For instance, a population could be all enrollees in all four-year universities in the United States, okay? And there could be millions and millions of students, correct, under study for that population, all right? A sample, on the other hand, is a smaller subset of a population. And usually your inferential statistical conclusion is at the mercy of, how well chosen your sample is from the parent population. For instance, let me give you an example. Suppose my population consists of all voters, registered voters in this country. Suppose my sample is, ladies and gentlemen, what if I'm really sloppy in selecting my sample? What if I only select CEOs of companies or corporations and basically only pull those people as far as a political issue is concerned? Do you think that sample is unbiased or biased? What would be your guess?
Biased.
Highly biased. I mean, because all I pulled were CEOs. Well, CEOs might be all on the same page as far as issues are concerned. Do you agree? So that sample's essentially worthless. All right. And so when you select a sample from a population, you want to make sure that every element in your population has an equal chance of being selected. All right. If that's the case, we call our sample chosen a simple random sample, which reduces or minimizes the bias that can occur from sampling results versus population results. Because when you do sample from a population along for the ride, inevitably always comes something called sampling error. Okay, you cannot get away from it. You can try to minimize sampling error, and the only way to minimize sampling error is, of course, to choose a good sample, a random sample, or to choose a sample that's very large and actually approaching the size of your population. In fact, if you choose a sample that actually is your population, would you have any sampling error with such a sample then? In trying to infer a population parameter result? The answer is no, because you've actually sampled the entire population. So why do we doink around with samples? Why not just measure everything in a population and be 100% accurate as to, what the population mean is, or the proportion, or the standard deviation or variance is? Why do we sample again? Anybody? Why do we have to sample?
So the data can be more accurate?
Well, to be more accurate, we would just pull it. We should probably just pull everything in the population. Do you agree? That way we wouldn't have to worry about any sampling error. Why do we have to deal with sampling? Why do we deal with it? Why not just pull everything in a population? What's the problem? I think I mentioned it about 20 minutes ago. What's the problem in pulling everything in a population? Let me give you a hint. Suppose my population consists of 10 million subjects under study, 10 million. What's the problem now? Why do we have to sample maybe from that population?
Is it because it'll be too big?
Too big. We may not have the time or the resources, ladies and gentlemen, to pull all 10 million subjects. It's just too big. For that reason, we have no choice. We got to pull out a smaller sample from the population and use that result to try to infer then what maybe the unknown population mean is, or the standard deviation or the proportion is. That's the reason why we sample, because it makes our life, tolerable. Now, granted, I mean, if your population only had like 200 subjects under study, you might as well just sample the entire population. Why mess around with a sample? Why have any sampling error? Okay, but normally our populations are huge compared to our samples, and as a result, we have to fathom something called a sampling error that occurs. But there are ways of controlling that error and minimizing that error, and you would discover that if you take a formal course in statistics. Math 150 here at Mott Community College is our formal introductory statistics and probability course. Okay, Math 150. So keep that in mind if you ever want to do any research, or for maybe your own individual needs or maybe a company's needs. It'd be wise maybe to take a course in elementary statistics so that you can see how to conduct a statistical analysis on samples. All right, there are 4 basic sampling methods. The first one is called a simple random sample. This is assuming that every object under study in the population has an equal chance of being selected when we select our sample. That's called a simple random sample. Normally, we abbreviate that as SRS, simple random sample. Another way of sampling, which is often used in industry in quality control, is something called systematic sampling. In which case we select like the kth element of a population. Let me give an example. In industry, suppose that a machine basically takes a spool of wire and basically rams that wire into like a header die and then creates like a bolt, okay, and cuts it, and the bolt then comes off the machine. Well, during the course of a day, this machine might crank out thousands of bolts from that spool of wire, thousands of bolts. And of course, fasteners are used in the auto industry to, fasten things together on cars and trucks and you name it. So bolts are extremely important in our everyday lives. They hold a lot of things together. Anyways, ladies and gentlemen, suppose that a machine cranks out like 10,000 bolts during a normal shift in a plant. Suppose that in order to sell your lot of bolts to, like to say, one of the big 3 auto companies, your bolts have to meet a certain specification, the diameters of which can only, deviate so much from a prescribed value. And if they do deviate further from that prescribed or required value by the auto company, then they will reject your lot and you will lose business and you're going to be going under. Okay, that's called quality control. Quality control ensures that the product that's being manufactured is within tolerance and within specifications so that the vendor will be happy and will continue to come back and use your product for whatever it is they're making, right? That's where quality control comes in. There's a lot of statistics in quality control. Suppose off this machine we survey, let's say maybe every 50th bolt that comes off the line. And with calipers, we measure the diameter, or maybe we have some other measuring instrument that we measure the diameter, or maybe the girth of the bolt, okay? Or maybe the density of the bolt, or whatever the trait is of the bolt. We got to make sure that it's within specifications so that the lot would be accepted by our vendor, all right? We'll continue to be paid by them and stay in business. All right, so systematic sampling is a classic example where we would choose like every 50th bolt off a machine or every 10th bolt. and we would measure it, okay? And then we use that sample to infer what might be the diameter of all of our 10,000s or maybe millions of bolts that come off that machine. All right, this is called systematic sampling. All right, other means of sampling would involve taking a population and dividing it into smaller groups. And these smaller groups, ladies and gentlemen, are called stratums. And then from each stratum, we would choose a simple random sample from each stratum. Okay, that would be an unbiased sample in the sense that you are basically polling subjects under study from each of the stratums, which are subgroups of the entire population. And because you're doing that, you're minimizing bias in your sample, as opposed to if you were just a sample like one area of your population and leaving all the other areas alone. That would be a biased sample, and it'd be worthless. All right, so stratified sampling involves breaking the population up into smaller subgroups, and then from each of the smaller subgroups, choosing a simple random sample. A similar way of stratified sampling is called cluster sampling, but there is a difference. Like stratified sampling, cluster sampling involves taking a population and breaking it up into smaller subgroups. But unlike stratified sampling, where in stratified sampling, we take a simple random sample from each of our subgroups, with cluster sampling, ladies and gentlemen, we don't do that. With cluster sampling, we randomly choose some of the clusters from all the clusters. Let's say we randomly choose, let's say we take a population and break it up into 100 different smaller subgroups called clusters. So there's 100 clusters. Let's say we randomly select 5 clusters. All right. Now, of the 5 clusters that are randomly selected, we would then poll every subject within each cluster. Okay. That's called cluster sampling. So the similarities again between stratified and cluster is that we take the population and break it up into smaller subgroups. That's the similarity. The difference is with stratified sampling, we take a simple random sample from every subgroup. With cluster sampling, we first randomly select some subgroups or clusters from all the clusters or the subgroups. And then we poll every element within each selected cluster or subgroup. So there's similarities, but there's differences between stratified versus cluster sampling. Both methods are pretty good in minimizing bias, though. So they're very effective methods in sampling. Hey, I got a question. There does exist something called convenience sampling. Which means, ladies and gentlemen, as it sounds, it means you basically collect a sample that's most convenient for you to collect. But just because the sample is convenient for you to collect, does that mean it's necessarily a good sample? Anybody?
Sounds like a terrible sample.
That's a terrible way to sample. You got it right. Convenience sampling is at the bottom of the list when it comes to effective, unbiased ways of sampling. Let me give an example. Suppose that, we're coming into an election. Suppose you want to poll, a group of people or some people, which you think is random on a particular issue. Let's say you stand outside the door of the General Motors plant. And when the shift changes, all the workers come out. You poll as many workers as you can get that come out of that plant about a particular issue. Do you think that sample is biased or unbiased?
I mean, depending on the issue, it could or couldn't.
Yeah, you're right. In general, we could argue that too. But in general, I mean, let me ask you this: the group of people that come out of that plant, that specific plant, do you think it's good? It's a good representation of the population in general?
No, it is not. It's just so little people.
I mean, it's just one sector, right, of people that work at that plant. It's biased. I mean, it's not allowing the average Joe to be surveyed out there in the population. And so, yeah, you got to be careful with your sampling. Your investigation, your conclusion, your inferential decision is at the mercy of your sample, the quality of your sample, ladies and gentlemen. So you want to make sure, if nothing else, that your sample is a simple random sample where every object in the population had an equal chance of being selected. That's very important. Now, there are calculators like the TI-84 that has a random number generator, a random integer generator. And so one way to choose a simple random sample is to number every element in the population from 1 to like 1,000,000 or whatever. And then use your simple random number generator on your calculator to choose a sample of sizes, maybe say 10,000. Those numbers that are spewed out by that random number generator on your calculator are, for all practical purposes, random, ladies and gentlemen. And that would be okay. Phone books. Do phone books exist anymore? Phone books. Now you're talking to somebody here that remembers phone books. That shows you how I'm starting to show my age here.
I saw
my
one up in Bertrand at the
Okay,
gas station.
they still got them out there, huh? All right.
It wasn't as large though. It was just
Yeah.
their area.
Yeah, I mean,
my family, they've got a couple of the older phone books, and they were like the thick ones. And
yeah.
I remember glancing over them as a kid, not really sure what some of it meant, but
Yeah, and you would look at like the last name Smith, and you would be bewildered as to how many Smiths there are. It just boggles the mind. Or like Jones or Smith. Smith has got to be one of the most popular last names. It has to be. I know it's not Ostermeyer. That's for darn sure. All right, my last name is not popular at all, at least in this country. I think it is in Germany more so popular. But anyways, ladies and gentlemen, yeah, phone book. One way to draw a simple random sample is to close your eyes, open up the phone book to a random page, put your finger on a name, and do you agree? You got a random chosen person. That would be okay. That's one way to choose a random subject. So any way you can randomize your sample is only going to be more effective in reducing sampling error. Okay, very important. All right, here's an example. Choosing a sample, 1 of 4. A student in an education class is given an assignment to find out how late typical students at his campus stay up to study. He considered 4 different methods of gathering data. Describe what types of sampling methods he's using in each case on the next slide. Then describe whether you think he is likely to get a good representative unbiased sample. All right, here we go. The first method, this person stops by the union before his 9 a.m. class and asks everyone sitting at a table how late they were up studying the night before. Ladies and gentlemen, do you think that's a good representative sampling? First of all, what type of sampling method is this? Do you think this is a simple random sample? Is it a systematic sampling? Might it be like stratified sampling or cluster sampling? Which one do you think this might be closest to?
Cluster sampling?
Yeah, we could argue this. Well, let's see. If it was cluster sampling, that means we would probably break our population up into different subgroups of different times of the days, though. Do you agree? Like this is what, before his 9 a.m. class. This is like one cluster.
I think this would probably be a simple.
Okay, if it's a simple random sample, that means that every student that attends this college or university would have an equal chance of being polled. You think that's the case?
Nope.
You know what type of sample this is kind of leaning towards, of which we did not even see on the previous slide. Which one does this sound like, ladies and gentlemen? The one I mentioned. Kind of sounds like maybe a convenience sample. Do you agree? It looks like this student's just trying to collect a sample before his 9 a.m. class. It looks like he's just doing this out of his convenience, correct?
It does, yeah.
It really has, a strong overtones of like convenience sampling here. Therefore, do you think that this sample, remember, and the issue is how late we're studying how late students stay up the night before. Do you think, in light of what we're studying here, that this one sample is biased or unbiased? What do you think?
I think it's biased.
I think this is horrifically biased. Stop and think, ladies. What about the students that stayed up really late last night, okay, and don't get with the program until 11 or 12 o'clock? Well, guess what? They have not been polled, and they never will be polled this way. Do you agree? Because this is an early morning 9 a.m. poll here. This is for maybe students that don't stay up late at night, correct? Don't get me wrong. There's probably some students that maybe stayed up late at night and did come to this union before 9 a.m. But in general, you got to admit, the students that stay up really late probably come to the union a little later in the day. Do you agree in general?
Yeah, that sounds about right.
Yeah, so yeah, I don't know. I think this sample's got a lot of bias with it. All right, let's throw this one aside. I don't like this sample. Let's try this next one. Okay, here's another thing that this person did. They asked the school registrar to give him a list of 50 students whose student ID numbers end in 4. The sample was 50 students whose student ID numbers end in 4. First of all, is this sample, do you think, any better than the previous sample?
No,
Not by much, if at all.
It's a little more random. Do you agree? In the sense the ID number ends in a 4. That's a little bit more random. What kind of sampling does this illustrate most closely? Simple random? Has the population been broken down into subgroups? Systematic? I don't think it's systematic. We're not polling every like 10th student in the university, correct? We're not polling that. So it's not systematic. This might be a little bit more closer to simple random sampling. Well, in a way it is not really fully, because remember, we're only choosing students whose IDs numbers end in a 4. So that kind of excludes all the other, ID numbers that end in something else. Do you agree?
Can I ask you something with
Yeah.
that then? With you saying it's not systematically, as in like students are getting pulled like that, wouldn't it kind of be because it ends in 4, so there is some type of system to it?
There isn't a way.
Is there like a hybrid type of
Yeah.
randomizer, or
Yeah. I mean, so far I haven't seen one that, adheres closely to any of the ones we talked about so far or have been exposed to so far. But what I don't like about it is that, we're only polling students whose IDs end in 4. I mean, what about all the other IDs that end in other digits? They're totally excluded from this investigation. Do you agree? That's what I don't like about this. But you can see that there's some gray areas here as to which one it adheres to. It's not clear cut and dry here, obviously. None of these methods have adhered to what we've been exposed to so far. Let's see if this third one is. Well, then this student surveyed the 5 people sitting closest to the door in each of his 5 classes. 5 people sitting closest to the door in each of his 5 classes. Yeah. That seems somewhat random. I don't know if people that sit closest to the door all have a common trait.
and my issue would be is there a seating chart or something? Could be
Yeah.
the same students in the same seats.
Could be. You know, let's look at D. Look at, and then the person said, look at the campus directory and choose the first name at the top of each page. Okay, this is for the first time, I think we finally see one that is obviously one type of sampling. What type of sampling is this? D. Chooses the first name at the top of each page. And there might be several pages in this directory. This kind of looks like what? It would be definitely what type of sampling? Systematic, do you agree? Because we're choosing the first name at the top of each page. This looks like systematic sampling all the way. So of all these methods, later, A through D, the only one that really clearly adheres to, it seems like adheres to the ones we've been exposed to. I don't know, it seems like the last one is the one that's most clearly in tune with systematic sampling. All the other ones are fuzzy at best. Somewhat fuzzy at best. So I don't know, if I had to decide, my life depended upon it, I'd probably go with D as being probably the most effective method of sampling of all these. That's one I would lean towards. But let's see what they say here. Yeah, well, this is what your author's thoughts here on A. Your author says it looks like it would be a biased sample because, you know, he's only polling students at a certain time in the morning. All the other ones are being excluded. And the second method is, you know, the last digit being a 4 is random. You know, I will give you that. But you know, depends how many students were on campus too. For a larger student body, you know, it would seem like digits and student IDs that end in a 4 would be more selective, more isolated from, in general, the entire student body, as opposed to if you had a smaller student body. So it kind of depends on that one there. Let's see about this next one here. No, they call that stratified sampling here. Let's see here. Let's see what C was again here. Survey the 5 people sitting close to the door in each of his 5 classes. Well, yeah, I mean, that's each of his 5 classes. There could be other classes that he's not taking though. But yeah, I guess, I mean, it looks like maybe the population has been broken down. His population has been broken down into his 5 classes.
But it still leaves the room for bias.
Yeah, it does. I mean, you got to understand that's his 5 classes, though. There could be a lot of other classes on campus. Do you agree that he's not even a part of? So, I mean, that's a little arguable here. But yeah, I mean, you could argue, yeah, a little bit that might be a form of, like, you know, stratified. Now, it would not be cluster sampling because he's not randomly selecting or not randomly pulling everybody in each class. Okay, he's just pulling out a simple random sample from each class, namely 5 people that happen to be sitting closest to the door. So yeah, it would not cluster. If anything, it would be stratified, but not cluster. All right. All right, let's see what D is here. Yeah, systematic sampling all the way. And again, ladies and gentlemen, my personal take on this is I would probably lean towards D as being probably the most unbiased sample of all of these. And then C would be the next unbiased. Okay. The worst sample would be A, in my estimation. That is probably the most biased sample. choosing only people at 9 a.m., especially since you're studying who stays up late. Yeah, it makes no sense. All right, so we at least, became somewhat familiar with the different ways of sampling. And again, your analysis really hinges in large part upon your sample and how unbiased it is and representative of your population it is.
If you don't mind me saying so, this does not sound like if you just let us loose and ask us in the next couple of minutes to do this, it doesn't sound like that I got good information.
For what now? For the
If you-
sampling methods?
Yeah, these examples and stuff, it just does not seem like I'm getting good information to understand this just yet.
Uh, um, yeah, and they're not really giving us a lot of good examples on this PowerPoint. There were a couple of examples, but unfortunately, these examples that it gave us were not in line or in tune with what it was we were, looking at, the 4 sampling methods. The only one that really was in line with one of the methods was D, systematic sampling, polling every first student on every top of each page of the directory. That's systematic sampling. But normally, in all honesty, as I was sampling, usually to draw a compromise between convenience sampling and unbiased sample. Usually the happy median between those two extremes is simple random sampling. All right, simple random sampling. And I can show you, like, this is a TI-84 calculator here, and it has a random number generator on it. Suppose our population consisted of like 10 subjects, each one numbered 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we had to choose a sample of size like 5, okay? And we wanted the sample to be purely random. Well, how could we do that? Well, there's Owen. Let's see here. Okay, wouldn't be there. All right, hold on. Well, on this calculator, if you hit your math button and you go over to your probability menu here, we have what's called a random integer generator here. And I'll show you how it works here. For instance, if I had a population that consisted of 10 subjects, my lowest numbered subject would be subject number 1. My highest numbered subject would be subject number 10. Okay. And suppose that I wanted to select one subject randomly from these 10 subjects. Well, this random integer generator would allow me to generate a random sample of size 5. For instance, my first selection, randomly selected from 1 to 10, would be 10. The second selection from 1 to 10 would be 10. Now, I would not use that again because that's already been selected. So I'd have to do this again, run this generator again. All right, 2. So 10 was the first randomly selected subject. 2 is the second one. And the third one would be 6. So we have a sample 10, 2, 6. We have 2 more to choose. 5. So 10, 2, 6, 5. These are all randomly generated. And we got 1 more. 8. So 10, 2, 6, 5, and 8 would be my sample of size 5. And that, for all purposes, is randomly generated by this particular function. Okay. So, that would take care of a lot of your sampling needs right here. Do you agree, this random integer generator?
Yeah, I got a question for you.
Yeah.
We were told, and for this class, it's a TI-30XS, and I know you don't have batteries, but do you know how to show us on that calculator how to use it?
On the TI-30XS, is there a random? Let me see if there is one for. You know what? On the TI-34 multi-view, I'm going to look at the TI-30 because you were specifying that. My batteries are dead, but let's see. On the TI-30 XS, I do have a probability button, PRB, which is probability. Well, guess what? I also have one on the TI-34. We have a probability button here, which is right there. You see that there, PRB? Now, when you hit that button, you have a probability menu where you have your permutation and combinations and your factorial function. Then you go over to random and you have a random integer generator there. See that there? Rand int. I would suspect that's probably the same on the TI-30. I couldn't imagine it being any different, okay?
Yes, it just was. Thank you.
Now, if you hit enter, now watch this. You hit 1, comma. I think you got to put the comma in here. My comma is above the decimal key. 10, close parentheses. If I hit enter now, watch this. I can randomly generate, say numbers between 1 and 10, integers between 1 and 10. Keep hitting the enter button and it keeps out spitting out what? Random integers. Do you see that? And this is cool because, I mean, suppose your population had, like 1,000 subjects in it. Well, you just have to type in 1, comma, 1,000. Each one numbered. Then you can generate a random sample, like 843 would be the first randomly chosen subject. 364 is the next randomly chosen subject. 813 is the next one. 229 is the next one. 112 is the next one. 894. And it's cool. These are randomly selected integers between 1 and 1,000 inclusive. Pretty neat, huh? So keep that in mind, ladies and gentlemen. If you ever have to do, any sampling, I would recommend you number your subjects in your population. Give each one an integer number, a positive integer number, and then use your random integer generator to pull out a sample of any size that you desire. It will be a random sample. So that's something definitely to keep in mind. All right. And so, like I said, a simple random sample, the one we just chose there, usually suffices in our needs, okay, as far as sampling is concerned. It's in statistics, elementary statistics, right? Some of these other methods, like I said, if you get into quality control and industry, they will have you probably select a systematic sample where you'll pull every kth object that comes off a machine and measure something of interest from it to make sure that it's within specifications, okay? But, for the most part, in this course, we're just going to choose a simple random sample. And I've showed you how you could do that using your random integer generator, okay? Ladies and gentlemen, there are two main branches of statistics. You have what is called descriptive statistics, and then you have what is called inferential statistics. Descriptive statistics involves going out into the field and collecting data, where, again, you could, or reaching into a parent population and pulling out a sample. Of course, you could choose a simple random sample, right? Then what we normally do with data is we try to organize it, either according to a table or some sort of a graph or picture. Inferential statistics has us going further. We reach into a parent population, pull out a good simple random sample, and then we use that sample to try to infer what an unknown population parameter result would be. And I already mentioned some methods, constructing a confidence interval or conducting what's called hypothesis testing, okay? All right, so that's basically what inferential statistics involves. For example, here's an example. The Bureau of Labor and Statistics estimates the number of people in the United States that are unemployed every month. Since it would be impossible to survey everyone, the Bureau picks a sample of adults to see what percentage are unemployed. Then they use that information to estimate the unemployment rate for the entire population. Now, to do this, we would be testing for an unknown population proportion of all people in the population that are unemployed by using our sample proportion result. You would probably want to either build a confidence interval or conduct formal hypothesis testing to do something like this. All right. We're not going to go that deep into statistics in Math 115. You will go quite a bit further in Math 150 if you take the course in elementary statistics here at Mott. All right, here's the first thing that we're going to use to try to organize our data. It's called a frequency distribution. A frequency distribution is a table. This table, the first one we're going to look at is called a categorical frequency distribution, or sometimes we call it a qualitative frequency distribution, in the sense that the data that is being organized is non-numeric. It is qualitative data, not quantitative data. Here's an example of a categorical or qualitative data set. 25 volunteers for a medical research study were given a blood test to obtain their blood types. The data is as follows. Now we will assume that the 25 volunteers selected were randomly selected here. So I guess, if you want to do justice to this, you would have a large pool of volunteers, and from that pool, you would randomly select 25. Okay. These are the blood types: type A, B, AB, or O. Okay. And of course, with blood types, you also have what's called an RH factor, positive or negative, but they're not including that here, just the blood types here. All right, here's what we're going to do, We're going to make a table. We're going to organize this data set. So this is our raw data we collected in the field. Let's organize it now. We're going to build what's called a frequency distribution table to do that. Notice my first column represents the blood type, A, B, O, or AB. The second column is going to be a tally count as to how many of these volunteers randomly selected fall into each blood type. And then the frequency column will add together our tally marks. So how many type A blood types did we select? Well, there were 5. There were 7 type Bs, 9 type Os, and 4 type what? AB. And of course, in the last column, we just add up our tally marks here. Ladies and gentlemen, you are looking at what's called a categorical frequency distribution table. It organizes your data into categories, in this case, blood types, and it gives you the frequency count of each category. Does that make sense how we did that for that data set there, how we built this table here?
Yes.
Pretty simple. This is pretty simple. Now, with these tally marks, a wise thing to do is that whenever you get to your 5th tally mark, you use it as a diagonal. Okay. That way, it's easy to count your tally marks when you have groups no larger than 5. Okay. Very easy to count your tally marks here. So, like if I had one more type O blood type, I would put what for my 5th for this group of 4 for the 5th count. I would put a horizontal mark because it's easy to count that. You got 10 of them, right? So yeah, always with the 5th count, always tidy up the group of 4 by putting the 5th count as a diagonal. Okay. Now another type of frequency distribution will involve, and normally this is usually the case, involves numerical data. And it's called a grouped frequency distribution, or a quantitative frequency distribution, in the sense that our data values are numeric or quantitative, right? All right, now the numerical data, ladies and gentlemen, are divided up into numeric classes. For example, if you gather data on the weights of people in your class. Now, there's a pretty good chance that no 2 people in your classroom will have exactly the same weight. I'm not saying it's not possible. It's certainly possible, but normally everybody has a slightly different weight. Okay, and because of that, we could actually build what are called classes, weight classes, like the weight class of 100 to 119 pounds, or 120 to 139 pounds, et cetera, et cetera. Now, this is the thing when you build a grouped frequency distribution. We need to remember a couple of things here. So there are a couple of rules here. Number one, you want to try to keep your classes down to about 5 or no more than 15 classes. Number two, this is very important. You want to make sure your classes never overlap. No overlap between your classes. Why do you think that might be important? For instance, if I had a class that ran from 100 to, let's say, 110, and then I got another class that ran from 108 to 118. What's wrong with these classes? Why is this no good?
You're counting them twice.
Yeah, we got overlap between these classes, and that's a bad thing. I mean, what if somebody weighs, let's say, 109 pounds? Do you agree? Oh, that's a big problem then. Because what class would we put them into? Because this person that weighs 109 pounds belongs in both classes, doesn't they? So, ladies and gentlemen, we cannot throw them into both classes because you're double counting this person. And data fabrication or data omission are the two cardinal sins of statistics. All right, that's a big problem. You never want to have overlap between your classes. All right, number three, don't leave out any numbers between the lowest and the highest class, even if nothing falls into a particular class. For instance, if this is my lowest class, 100 to 110 pounds, what happens if I have somebody that weighs 80 pounds? Well, they will be excluded from this distribution table. Do you agree? And that's a bad thing. And so, we don't like to exclude any data points, and we don't like to double count or triple count data points either. All those are terrible things to do in statistics. So you want to make sure that your frequency distribution table is robust enough to, encompass all of your data that you're trying to include. Number four, make sure the range of numbers included in a class is the same for each one. In other words, what this is trying to say, ladies and gentlemen, is that you got to make sure that all your classes have the same width. The same width. They're all equally wide. Why do you think that's important? I'll tell you why. What if I had a class that went from 100 pounds to, let's say, 100 pounds to 250 pounds? And let's say I had another class in my distribution that went from 251 pounds to 253 pounds. What's wrong with this, ladies and gentlemen? What's wrong with that?
It's not the same amount of numbers.
Yep. So which class is going to hog up just about all the data?
The 100 to 250.
That's right. The 100 to 250 pound class is so wide that it's going to hog up just about all your data points. You might not have any, if any, in the 251 to 253 pound class. So this is going to do a grave injustice to trying to organize your data. All right. Always make sure each class has the same width. Very important. So no overlap between classes, same width. Make sure that your frequency distribution table allows for including all your data points in your investigation. All right. This last thing here, the beginning and ending values have to be chosen based on how the data values are rounded. Well, this is indicating that your endpoint values of your class need to be somewhat indicative as to what type of data you collected. For instance, if you collect data that is all rounded off to the nearest tenths, okay, then, you might want to maybe think about having your class limits or endpoints rounded also to the nearest tenth. Okay, but the big three are these right here. By all means, make sure that your classes do not overlap. All right, make sure that every data point has a place in your classes somewhere. And this one here, make sure that the classes all have the same width. Very, very important. Okay. All right, so these are the big three, or the three bases that you want to make sure you cover: 2, 3, and 4. Very important there. I always check for these three things here when I'm looking at a frequency distribution table. Those are the first three things that I always look for. Are there any classes that overlap? Has any data point or data points been excluded from all of your classes that you've collected? Do all the classes have the same width? Those are the three things that I always focus on. And usually, you know, I mean, if a student has all these three bases covered, as far as I'm concerned, is their distribution is just as accurate as anybody else's distribution. Whether you choose to use 5 classes or 6 classes or 4 classes, that's not really so much of a major issue as these issues 2, 3, and 4 are. Okay. All right. All right, here's another example. The data represents the record high temperatures for each of the 50 states in degrees Fahrenheit. Construct a grouped frequency distribution for the data. This is numeric. And ladies and gentlemen, it's a rather large data set. But can anybody show me or tell me what the minimum data value in this data set is? The minimum?
Is it 100?
Yeah, I'm looking at 100. I think that's the smallest data value in the data set. I think that's your minimum observation. What would be the largest one, the maximum observation?
$122.
I see one larger than 122. Keep your eyes going. So what is my maximum data value?
134.
Yeah, it's tucked right up here. Kind of looks like it's 134. I don't see anything larger than 134. So there's the max. And this is your minimum data value in your data set. Okay. So ladies and gentlemen, when you build a frequency distribution table, you want to make sure, you know, that your lowest class, okay, goes down low enough so you can include 100. In other words, if your first class starts out at 105, no good. Because if your first class starts out at 105, then 100 will not be found in that first class. In fact, 100 will not be found in your distribution anywhere. And that's one of the cardinal sins I mentioned on the previous slide. So make sure your first class goes down to at least 100. Now, whether your first class starts at 100 or your first class starts at 99, no big deal either. You got wiggle room there, okay? Because at least your first class will contain the smallest value in your data set. And just make sure your last class contains your maximum value. So you want to make sure that the last class ends, you know, no lower than 134. In other words, if your last class ends at like 130, guess what? 134 will be excluded from your distribution, and that's no good. So you got to make sure your last class ends at least at what? At least at 134. Now, maybe you'll decide to end your last class at 135 or 136. That's okay. Is this making sense here, ladies and gentlemen? These bases that we want to make sure are covered for frequency distributions here. Very important. Okay. Now, they took the maximum and the minimum values and subtracted them, and they got 34. 34 is called the range of your data set. We call this the range. It's the difference between the maximum and the minimum data in the data set. The difference between the max and min value in the data set. The range. All right. Now, suppose that we want each class to be 5 degrees wide. And if I divide 5 into 34, about how many classes would I have? Well, 5 does not divide evenly into 34. It divides in 6.8 times. But, ladies and gentlemen, we got wiggle room here, okay? As long as those 3 criteria on the previous slide are satisfied, you have a little bit of wiggle room here, right? For instance, you could probably bump this up and call it maybe how many classes instead of 6.8 classes, which is ridiculous. Call it maybe what, 7 classes? Suppose we maybe use 7 classes in our frequency distribution here. Now, what's our lowest data value? 100. So you got to make sure that your first class starts out low enough to include your minimum data point in your data set. All right. Suppose that you start your your first class off at 100. And then maybe you take it up to 105. Okay. That would be a good way of starting out your classes. That would ensure that all the bases are covered that we mentioned. So let's see what your author has done here with these decisions here so far. All right. Now, your first class, your author decided to go from 100 to 104. 100 to 104. Now, I have a question for you, ladies and gentlemen. How do we determine the width of each class? Here's how we do it in statistics. One way is to take the difference between successive lower endpoints of adjacent classes. So we could say the width of this class, of all these classes, is equal to 5, indicative of the first values I got boxed in. 105 minus 100 is 5. And notice that's the case for all these. 110 minus 105 is 5. 115 minus 110 is 5. 120 minus 115 is 5. 125 minus 120, 130 minus 125 are all 5. That's one way to determine the width of a class. Another way to determine the width of the class is by looking at the difference between successive upper endpoints of each class. 109 minus 104 gives you a width of 5. 114 minus 109 gives you a width of 5. 119 minus 114 gives you a width of 5, etc., etc. So whether you want to look at the difference between adjacent lower endpoints or upper endpoints, doesn't matter. You should have in each case the same width of 5 in this case. Okay. So each class is 5 units wide. All right, ladies and gentlemen, is there any overlap between any classes? Any overlap? Does there appear to be any overlap? Doesn't look like it. Do you agree? Doesn't look like it. Doesn't look like there's any overlap. Now, I have a question for you. What if you have a temperature that measures 104.3 degrees? Or I'll tell you what, let's make it even trickier. What if we had a temperature that measured 104.5 degrees? Question, what class would it belong in? First or second? All right, here's what you do in a situation like this. You have to come up with a rule. And ladies and gentlemen, the rule that I establish may not be the same rule that you establish. That's not important. What is important is that when I establish a rule, it must be, okay, applied faithfully to each of my classes, not to just a couple of classes in my distribution. As long as I faithfully apply my rule to all of my classes in my distribution, my rule is just as accurate as your rule is, so long as you apply your rule faithfully to all of your classes. So my rule could say this: for a data value that is 100, that has the 0.5 ending or less than 0.5 ending, my rule might say included in the previous class. That might be my rule. So like 104.5 maybe will go in my what? Will go in this first class here. So that means, ladies and gentlemen, if I had another observation in my data set that measured like 114 point what? 4, what class would it go in based on the rule I established? Would it go in this class here, the first class, or the second class here? Where would it go? Based on the rule I've established.
The first class.
I would have to go in this one, exactly, because my rule that I established says that as long as a temperature has a 0.5 ending or less than 0.5 ending, I will throw it in the first class always. So my 114.4 would go in this class. That might be my rule. But your rule might be different. Your rule might say if a temperature ends in 0.5 or larger than 0.5, you'll throw it in the next class. Your rule might not throw the 104.5 in this class. It might throw it in what? This class. That's okay. So if you run into a temperature that is 114.6, then where would you have to put it? 114.6 according to your rule. Would you put it in this first class here? No, you'd have to put it what? In the second class. So the key is your rule might be a little bit different for dealing with decimals as far as deciding what class you're going to throw it in than my rule. But as long as we apply our rules faithfully to all of our classes and to all of our data points, our rules are just as accurate. Okay? Is that making sense there? All right. Is there any other violation with these classes here? There's no overlap. The classes have the same width. It looks like my minimum data point will be found in the first class and my maximum data point of 134 will be found in the last class. So we're not going to exclude any data points. That base is covered. It looks, ladies and gentlemen, like we have a very valid frequency distribution table here. Looks like this is a good, accurate distribution table. No problems whatsoever with it. So we'll go with it. All right, so how many temperatures, high temperatures were in the first class? 100 to 104 degrees. Well, you'd have to go back to your raw data set and count how many temperatures were between 100 and 104 degrees. Well, here's one. There's one. Any others? 100 to 104. Oh, here's 104. There's one. Any others? 100 to 104 degrees. Did I miss any? Were there only 3? I think there might have only been 3, agree?
Yes.
And there are, ladies and gentlemen. You see that? And then you would do that for all your other data points, determining what class they fall by putting a tally mark in the respective class. Then, of course, the last column is your frequency column, where you actually add up your tally marks. You now have what is called a quantitative frequency distribution table that organizes your data. Now, from this table, just one quick glance at this table. What was the most common record high temperature? The most common. Boom, you can ascertain that very quickly by looking at the table. What was the most frequently occurring high temperature class?
110 to 114.
Yeah, 110, 114 degrees. You see that? You see how powerful this table is in helping us to answer a question like that very quickly, as opposed to sifting. Look, what if I asked you that question and I wanted you to sift through the raw data to determine the answer to that question? Now, wouldn't that be a mess? Could you imagine trying to sift through all this data and answer a question like that? Could you imagine, even if this data set had maybe thousands or millions of data points in it, how horrendous that would be to do something like that with your data all out of order? Tables and pictures and graphs, ladies and gentlemen, are invaluable in conveying a lot of information very quickly, very quickly. So it's critical to be able to organize our data. All right. What was the least frequent record high temperature class? Well,
130 to 134.
130 to 134. I mean, that was the least frequent, okay? So again, this table is invaluable. All right, let's show you one more plot that can also help us organize our information. It's called a stem and leaf plot. The stem and leaf plot basically has us taking our data set and dichotomizing it, ladies and gentlemen, into two portions. One portion is called the stem portion. The other portion is called the leaf portion. All right. Now, what portion you call your stem versus leaf portion really depends upon how the data presents itself to you. Okay. For instance, if you have data, ladies and gentlemen, that's in the tens and hundreds, you might want to call your stem portion maybe like your tens digit and your leaf portion your ones digit. Okay. For instance, here's a data set to illustrate this. Oh, this is interesting. It's actually an authentic data set. It says percentage of adults that had been fully vaccinated against COVID-19 as of July 1st, 2021. Draw a stem and leaf plot illustrating these data. So based on, how the data presents itself, notice we got data that ranges from what to what. What's the smallest observation in this data set here? Just by taking your eyes and scanning through it quickly, can you kind of see the smallest one?
It looks like 33.
That's what I'm gathering. And the largest looks like about
66.
66? Okay. So our data ranges from the 30s, the 40s.
Oh no, we got a 30.
Whoa. Okay. I sit corrected. There's a 30. There it is. It lurketh in there. Okay. Do you agree, ladies and gentlemen, our data ranges from the 30s, the 40s, the 50s, and the 60s? Because of that, it would probably seem natural, okay, to call the stem portion of your data the tens digit and designate the ones digit as being the leaf portion of your stem and leaf plot. Okay, let's show you how to build a stem and leaf plot now. So taking this data, we're going to show you how to build a stem and leaf plot. The stem portions will be the tens digit, just like I mentioned. The 30s, the 40s, the 50s, and the 60s. Notice, very important, the stem values must strictly increase from top down. That's very important. They must always increase from top down. That's critical. If they don't do that, your stem and leaf plot's not correct. Now, the leaf values will run from left to right. They're going to be the ones digits. They must strictly increase from left to right. That is critical. Because we have this strict ordering of our stem versus leaf portions of our data values, ladies and gentlemen, we have a lot of order and structure in this particular graph here, which is going to facilitate our ability to answer important information and questions regarding this data, rather. All right, so here we go. Let's finish this now. So we had a temperature that measured what? 30, do you agree? We would put a 3 and a 0. We read this as 30. What was the next largest temperature? Whoops, hold on a second. What was the next largest temperature? We had a 30, and then we had a, you could cross this one off when you accounted for it. 30, and then a 33, it looks like. We only got 133, I think, in here. I think so. 133. So then, ladies and gentlemen, you would put a 3 here. So we have a temperature that measured 30 degrees, 33 degrees. What's the next higher one after 33 degrees? Again, mark this one off. We've accounted for that. After 33, I see a 34. Is there more than 134 in here? I only see 134, don't you? And so I will have a 30 what? 4. What comes after 34?
35.
Yeah, how many 35s? Here's one. There's what? Two. Oh, here's one. Here's one. 35. Looks
Push.
like is there another one?
Yeah, and next the
Yeah,
third.
there you go. There you go. Yeah, it looks like there's three. Okay, looks like there's 335. So you know what I'm gonna do? I'm gonna put how many fives? 3. 35, 35, 35. Do we see how this is working, ladies and gentlemen, with the stem and leaf plot? Okay, notice stems increase top down, leaf values increase from left to right strictly. All right, let's go on and see how they constructed the whole darn thing now. Wait a minute. They didn't even construct the whole thing. What the? Wow. Are you kidding me? They didn't even finish this thing here. That's lame, isn't it? All right, but do you get the idea how we would do that? Let's see if I can bring that data set over here. I'd have to snip it here. I find that rather amazing that they did not actually finish that stem and leaf plot there. Unbelievable. Okay. Maybe we can finish it, huh? All right. Okay, ladies and gentlemen, we had a 33. What else? We had a 33, right? How many 34s were there? What? How many 35s? I think there was 3.
You're missing the 30.
Son of a gun. You're right. I'm missing a 30. It should be a 0 in there. All right. Let's see. I accounted for the 34, the 30, the 33, the 35s. There were 3 35s. What comes after 35?
36. It's yeah, second row.
36. How many 36s we got here? It's gonna get easier later on the further we go on with this. You can see this. Now it would be nice if we had a utility that could sort our data. Do you agree? There are calculators that can sort data. Can our machines sort data? Let me see. Can we sort data on this calculator here? Can we sort data? Well, we can enter data in. As far as sorting data is concerned, I'll have to get back with you on that, whether we can sort data or not, but usually our data sets are small enough where we can manage them, okay? But you can see where this could get way out of hand for large data sets, obviously. In that case, you definitely want to have, maybe some way of scanning your data in quicker into a computer system, because then a computer could order it very, very quickly. Computer could order like 20 million data points within a fraction of 1 second. Okay. Do we have any more 36s other than 1? What comes after 36? Do we see it? I see a 38. I see a 37. I see 2 37s.
There's 3 37s.
There's another 37. You got it right there. Okay. What comes after 37? I see a 39. I see 38. 38 occurs only 1 time, right? That's it. How many 39s we got? Looks like we got quite a few. We got 1. Okay, so we got 1, 2. Any other 39s? Up 3. And that's it, right? Think so? All right, 80-40. I don't see a 40, 41, right?
It's a 40 in the fourth row.
Oh, there is. Fourth row. Oh,
Second row with all the slashes in line.
right here, 40, there you go. 40, 41. Got one at least. Any other 41? I don't see any. All right, 42. Yeah, I got a 42 here, at least one. Any other 42? There's a 42.
Yeah, there's another one.
There's another one. And let's see, 43. 43. Got two 43s here. All
There's
right,
3 43s.
another 43. There's another one right there too. All right, any other 43s here? 45, 44. Got a 44 here. All right. Any other 44? Okay, so we're kind of getting the idea. Any 45s here? I got one here at least. Here's another one. And any others? I don't see any 46. I got at least one 46 here. And there is another 46 here. 47. We got 147. Any other 47s? I don't see any. 48. We got a 48. Yes, we have a 48. Any other 48s? No, I don't see any 48s. Okay, 50. Do we have a 50? Oh, wait, we got 40, 49. Hold on a
There
second.
was 2 48s.
There's another 48. So oh my God, there's another one there. Yeah. All right, any 49? No, any 50. Yep, here's a 50. Any, here's another 50.
It's 2 more 50s.
There's another 50. And there's one more somewhere in here lurking around. Where are you? Right here. All right, at 51. I don't see any 51s. 52. Yep, got one. Another one. Yeah, another one.
It's one more.
And one more. $52. Oh, yeah. 53. Doesn't look like it. 54. Yeah, got one. 50, another 54. 55.
There's one more
There's
54.
54.
And another 54 right here. Now 55. 55. 55, another one over here. Another one down here. All right, 56. Yeah, 56, two 56s. All right, 256s, any others? 57, 58, 59, got a 59 here. 59, right, 60, no, 61, got a 61. 62. 62. And 63, 64, 65, 66, we got 66. I think we're done. Okay. But in general, that is called a stem and leaf plot, and therefore, we can now, use a stem and leaf plot to maybe ask some questions. What did these values even pertain to again? These data values? What were they? What do these data values even pertain to? Oh, number of people that are vaccinated. All right. So we can see that the percentage of adults that have been fully vaccinated, right? (62%, 62%). So how would you interpret these numbers here? It's the percentage of adults that have been vaccinated since July 21st. July 1st, 2021. How many observations are even in this data set here? There's 50 observations, correct? So how would we interpret these numbers here? Like, what is 44%? That differs in 45%. I'm still not understanding the data. I mean, I know these are percentages, okay, but for what? I mean, are these over different days or something, or different months, or what's going on here? We got all these different percentages, correct, of adults that have been vaccinated. Normally it would be like, what was the percent of adults that were vaccinated in like July? Then what were the number of, what was the percentage of adults vaccinated by the month of August, et cetera, et cetera. But what do all these percentages represent? There's 50 of them. What is that? What does the 50 mean? What are the 50 different percents? That's what I'm hung up on. Anybody know? Want to lend some insight? Percentage of adults that have been vaccinated since July 1st, 2021. There's 50 observations in this data set. But I guess I'm a little hung up as to what all the different 50 represent. But anyways, we understand the stem and leaf plot, how it was built, correct? That's the important thing. All right. Now, normally when you see a stem and leaf plot like this, you're not going to see these little numbers up here, okay? I've never seen them ever before in any stats book. Never seen them. Why are they there? Well, they're there just to indicate at what value your leaf value begins with for each of the stem category. For instance, the first leaf value starts off at 5. The first leaf value here starts off at 0. First leaf value here starts off at 0. First leaf value starts off here at 5. First leaf value starts at 0. First leaf value starts at 5. Do you even have that? Do you even need to have those numbers up there? The answer is absolutely not. You don't need those. You can still see, if I was asked this question, how many data values were 110? Notice the stem portion consists of the ones and the tens digit here. No, the tens and the hundreds digit, excuse me. So, and you see this little key down here. Like, this shows you how to read the stem and leaf plot. Sometimes they have a key here. That 10 with a little elevated 0 and the vertical bar 4, you just read that data value as 104. How do you read this 10 with a little elevated 5, vertical bar 6? You read it as 106. You don't even need these values here. They're not necessary. So how many data values measured 100? You would say how many data values measured 100? There were 2 of them. 100, 100. How many data values measured 118? 118. 118 occurs how many times? 1, 2, 3, 4, 5, 6 times. There's 6 118s in this data set. How many data values had a value of 134? 134. There was only 1. How many data values had a value of 122? 122. There's only 1. Do we understand how to read this stem and leaf plot here? How many observations were 114? 114. There were 4 of them. Okay. All right. Well, we don't have much time left. That is obvious. But in the time we have left, maybe we could do one problem. This is section 11.1. As always, you'll feel free to look down through the examples in this textbook here. It can only help things out. All right. They give you some examples of stem and leaf plots there. See them there? Stem and leaf plots. All right, ladies and gentlemen. Let's see if you can do number 25. 25 fans of reality TV were asked to rate 4 shows, and the data below reflect which one each rated highest. Construct a frequency distribution for the data. S stands for Survivor, D for Dancing with the Stars, B, Big Brother, A, The Amazing Race. They just want you to build a frequency distribution table for this data set. Okay, go ahead and do that. That shouldn't take too long. Go ahead. We'll call this classwork 1. All right, let's take a look here. So this would be a frequency distribution table for that data. The order in which you list these particular shows from top down does not matter. Order doesn't matter. But basically, it's just indicating the frequency or the frequency in which each show is chosen. Anybody get something like that? That's called a frequency distribution table.
Yes.
That's all there is to it. Now, we don't have time to do number 27, but it says the ages of the signers of the Declaration of Independence are shown here. Age is approximate since only the birth year appeared in the source. And one has been omitted since his birth year is unknown. Construct a frequency distribution for the data using 7 classes. Let's just look at the answer, ladies and gentlemen. They actually build a frequency distribution using 7 classes here, and you can see them right here. Notice there's no overlap between classes. What's the width of each class? Can anybody tell me what the width is?
6 years.
34 minus 27 is 6. Or you could have done the difference between successive upper limits, 54 minus 47. Wait a minute. No, it'd be 7, correct? 34 minus 27 is 7. The width is 7. 54 minus 47 is 7. Yeah, these classes are 7 units wide. All righty. And notice no data points been excluded. They'll usually tell you, like on Alex, they're going to tell you how many classes they want you to construct. Okay, so don't worry about that. They'll tell you how many. And they may even indicate what the lower endpoint needs to start off at. Normally, we start the lower endpoint of the first class off at the minimum data value in your data set. Okay, and then you go from there. So if these classes are to be 7 units wide, you go from 27 to 30, 27 to 34, and then 34 to 41, 41 to 48, 48 to 55. Okay, and then 55 to 62, 62 to 69. Then the upper endpoint, just make sure it has to be 1 less than the lower endpoint of the next class. So like 33 here, okay, is 1 less than 34. 40 is 1 less than 40. 47 is 1 less than 48. 54 is 1 less than 55, et cetera, et cetera. All righty. All right, so today what we did is we began to open the door a little bit with statistics. We differentiated between a population and a sample. We looked at some ways of sampling, and I indicated that the most prevalent, most common way of sampling is just a simple random sample. We also looked at how to organize the data in the form of a frequency distribution table or as a stem and leaf plot. Okay. And so we're off to a good start in basic statistics. All right, ladies and gentlemen, that is it. I will try to open up that aforementioned quiz. If I'm late in doing that, I'll just extend the due date, check your email. I'll be on the line for a couple minutes if you have any questions or concerns. Have a good day.